Before considering a slightly more interesting example of a principal value integration, let's talk a little bit about this very concept. And it's probably better to start with the simplest possible example: the integration from -1 to 1 of the function dx over x. Taking as it is, this expression is meaningless because the integration contour passes right through the first order pole of the integrand. But on the other hand, the integrand is an odd function of x and the integration domain is symmetric, so there is a temptation to prescribe a zero value to this expression. That kind of examples provoked the introduction of the so-called Cauchy principal value of the integral, and it is introduced as follows. We simply split the contour at the singularity, then we insert an infinitesimal separation centered at this singularity. So the principal value of this integral is deciphered as the sum of the integrals from -1 to -epsilon plus the integral from epsilon to 1 dx over x, where epsilon is set to 0 at the end of the calculation. And indeed, one obtains logarithm of epsilon for the first integral and logarithm of 1 over epsilon for the second integral. Summing them up, we already obtain 0, and of course setting epsilon to 0, we obtain the 0 answer. And now let's study a less trivial example. Compute the principal value integral from -infinity to +infinity e to I bx over x squared minus 1 dx, where b is negative. First of all, we see that our integration contour passes through two singularities of the integrand, which are simple poles at points x is equal 1 and -1. As a first step, let us draw the contour. It is split into three pieces, and let us decipher the principal integration sign at the sum of the integral from -infinity to -1 minus epsilon, plus the integral from -1 plus epsilon to 1 minus epsilon, and plus the integral from 1 plus epsilon to +infinity. Naturally, to employ residue theorems, we need to close the contour somehow. And minding the future application of Jordan's lemma, we connect the infinite edges of this contour by a lower infinite semicircle, CR. Next, we connect the adjacent pieces of the contour by two infinitesimal lower semicircles centered at point -1 and 1. The next step is to promote our function into a complex plane. Let's denote it f of z. And consider a closed contour integral of f of z. It is naturally split into our original principal value integral plus two infinitesimal integrals around semicircle centered at point -1 and 1, and plus the integral along the lower infinite arc. Now the integral along the lower semicircle vanishes due to Jordan's lemma, because our increment b is negative, and our pre-exponential function, which is 1 over z squared minus 1, decays uniformly with respect to its argument as z tends to infinity. Next, the closed contour integral itself. The function f is obviously regular inside this contour, so the closed contour integral is also equal to 0. And thus we obtain our principal value integral at the sum with minus sign of two infinitesimal integrals round our semicircles at point 1 and point -1. And we compute these infinitesimal integrals with the same technique outlined in the previous video. We simply Laurent expand our integrand in the vicinity of -1 and 1. So let's do the calculation for the left semicircle. We introduce a change, z equals -1 plus epsilon, and build a Laurent expansion of our function, f of z. F of -1 plus epsilon is equal to, in denominator we'll have minus to epsilon, while the denominator yields e to minus ib, plus the regular terms. Now the integral is equal to -1/2 times e to minus ib times the integral of d epsilon over epsilon. This integral is computed via standard parameterization. Epsilon equals modulus of epsilon times e to I phi, where phi changes from pi to 2 pi. The evaluation is straightforward, and we obtain I pi. So the integral along the left semicircle is equal to minus I pi by 2 times e to minus ib. Now the next integral. Again, we perform a Laurent expansion of our integrand in the vicinity of point 1. Z equals 1 plus epsilon and f of 1 plus epsilon is equal to e to ib over 2 epsilon. And we perform the integration. 1/2 times e to ib times the integral of the epsilon over epsilon. The integral is taken with the same parameterization and naturally yields the same I pi. So the second integral is equal to I pi by 2 times e to ib. And as a result, our principal value integral is equal to I pi by 2 times e to minus ib minus e to ib. Now this combination of exponential is reduced to a sine function, and we obtain pi times sine b. And that's it. That completes our initial discussion of the integration methods of complex analysis, and I hope to see you the next week.